So last week we talked a lot about blockchain evolution and how Bitcoin is can be changed, what can be updated, what about consensus, what about the network itself, hard fork, soft fork, signaling, all the stuff. And I think that's really interesting to look at that because it's the part of a viable network, and obviously we describe the processes as they are meant to be, but it can be the case, or it is sometimes the case, that the technology itself or the network itself behaves a little bit different. So this is all very this is how it's supposed to work, but sometimes there's also a little bit variance in there. Okay, so let's take a look at the first question here about blockchain evolution. And this is a task, I think, or this is a question, and I also mentioned this last week, that I would recommend to do this on your own. So that's really a great exercise to understand what's going on in the consensus layer and what is consensus relevant and what's not. So let's take a look in there. What I also wanted to mention is this, that these methods or data structures that are relevant to the consensus are not only relevant for Bitcoin, but obviously this applies to other blockchains as well. So if you take a look at Ethereum or at Hyperledger or at Corda, this could be the case that similar mechanisms are there, and these similar mechanisms lead to also the relevance for the consensus layer. So let's take a look. We have 6 parts here, and the first one is so the question: explain the implications of changing consensus relevant methods or data structures. Decide if following changes to the Bitcoin software would impact the consensus layer. So we take a look at these changes here and decide whether they would impact the consensus layer or not. And let's start with the first one. So transactions in the memory pool are deleted after a certain elapsed time. So usually when we look at the memory pool, it's the pool where unconfirmed transactions are in there. Unconfirmed transactions mean we have valid transactions which are not included in the blockchain yet. And as I showed you last week's, it can be quite messy on the blockchain. So maybe a lot of transactions are there. Many people try to create transactions, so that can be a little bit of a traffic jam, so to say. And this idea is to say, okay, after a certain time, we just remove transactions out of the memory pool. The part here is that the memory pool itself is a subjective data structure, so to say. So each node has its own memory pool of transactions, and there is no right or wrong there, which transaction should be in there or which not. So if you're a full node, or if you're even a miner and your memory pool is empty all the time because you do not allow to add new transactions to that, so obviously this wouldn't be that wise, but you could do that, then your network wouldn't harm from that. So it would not impact the consensus layer. Why? Because it's subjective to you and it has no impact on how the network decides if blocks are valid, if transactions are valid. So that's the first point here. And that's up to you, that's up to your software. And the network is not dependent on that. Also, you have to think about, does this influence? We can separate this a little bit in 2 parts. So first of all, is this Bitcoin software implemented for everyone or only for your computer? So obviously that makes a little bit of difference, but I will go to that if we come to a point where it's worth discussing. The scheme for transactions is changed such that the transaction fee is explicitly stated. So the scheme for transactions is changed such that the transaction fee is explicitly stated means that we have a in our transaction, usually the transaction fee is stated via the difference between the transaction inputs and the transaction outputs. So if you put 10 Bitcoins in and only spend 9 of them, this 1 Bitcoin is, so to say, the transaction fee. And now you could basically declare some kind of additional transaction output, which clearly specifies that this amount of money should go to the miner as a transaction fee. You could do that, and definitely would impact the consensus layer. Why? Because this is non-standardized. This is nothing that the network is currently aware of, this idea. And if you would include transactions like that, then you would likely get invalid transactions, or the transaction itself would be not included in the blockchain because they have no transaction fee, no original transaction fee in there anymore. So obviously, if every node would implement this, if every software would implement this, then you have to think about how you're going to update to that. But definitely it would also work for every. So if the network agrees to that this is the new rule and this is the new system, then it would work, but it is definitely impacting the consensus layer here. The next one is, after receiving and validating a block, the node encrypts the data before storing locally off-chain. And the data is decrypted before being sent to other nodes. This is also a example where only you on your local end is doing something that the network doesn't see that anyhow. So if you would say you encrypt the data you receive before storing it off-chain or locally, then there is no harm in doing that. So you could do that. It's basically meaningless to do that because obviously this data is available to the public. But if you then decrypt it before sending it to other nodes, then it's fine. So not impacting the consensus layer because other parties do not really are influenced by that. The next part is the node enables a new method, RPC call, in which the user can search for stored text on the blockchain. So a little bit reminder, using the proof of work, the op return opcode in Bitcoin script, you can use, you can basically store data in your transactions. And that's actually done very often. And you could now enhance your local Bitcoin software or Bitcoin node to say, okay, I can read from this blockchain. And you can do that. That's now not really difficult. And but it would not impact the consensus layer. Why? Because it's just reading here. So there is no writing to the blockchain. There is only reading, and having locally RPC calls does not really influence how your node behaves or how other nodes behave. The next one is Bitcoin script now supports an opcode which introduces loops and jumps. So this would need to be now supports multiple opcodes which introduces loops and jumps, but it'd be interesting to see one opcode which can do both. But apart from that, changing the Bitcoin script is something that definitely impacts the consensus layer. Why? Because other parties now have to decide if a opcode is valid or not. So if you would include some kind of Bitcoin script which includes these new opcodes, then other parties would not be able to verify it. So if you would implement it on your own and create transactions with it, you're very likely to get rejected. So that's something worth mentioning here. But also, again, if this change is applied for everyone, then obviously it would work. And the block size, the last one, the block size is increased from 1 megabyte to 1.5 megabytes. So that's obviously something we already discussed in the lecture with Bitcoin Cash, Bitcoin Gold, Bitcoin Satoshi Vision, all these forks or all these chain splits from a Bitcoin, from the main Bitcoin, from the original Bitcoin, had some kind of block size changes here. And in this case, that's also a change to the consensus layer, and it would impact the consensus layer, because if you create a block which now has 1.5 megabytes, then it's going to get rejected if the other nodes have not updated their software. Okay, one question on tweetback. We're going to answer this really quick. Usually the transaction fee goes to the address of the Coinbase transaction. Yes, not usually, but every time. So the Coinbase transaction specifies an address, and to this address the mining reward plus Coinbase plus transaction fees is sent. Okay, next exercise. Assume that the Bitcoin development team plans to increase the maximum block size limit from 1 megabyte to 10 megabyte. Explain if this change requires a hard fork or a soft fork, and explain the risks of changing this property only. But this is a really nice question, because I think there's something a little bit to unwind here. So if we think about block sizes and hard forks and soft forks, and I like to make a little bit of an example. I like to talk a little bit about that, because I think there's a lot of misunderstanding, and I received a lot of questions last week on tweetback about that. So maybe we can elaborate a little bit on that. So if we look here, so what is a hard fork? What is a soft fork? Hard fork usually describes, so I would do a little bit of Venn diagram. So we have allowed states. So this is our original 1 megabyte set of states. So you have to get a little bit creative with that, but in these are all possible blocks. So they're basically almost indefinite amount of blocks, which adhere to these rules, to these 1 megabyte rules. And if you now would create a rule, so this has some kind of, there is a certain amount of, some number is there for allowed blocks. So we call it X here. And if we would impose rules that would limit this set, so if, for example, if we have something like I would say, okay, we just allow not too easy to handle this here, to split this in half, so to say, and we only allowed 0.5 megabyte. Then this is the new, this would be another state. So obviously it would not be the half, it would be a little bit less. But this reduces the state of allowed blocks. So it does not extend it, but it does decrease it. And so there are blocks which adhere to the 1 megabyte rule, but they also adhere to the 0.5 megabyte rule. Why? Because, for example, they are 0.3 megabytes large. So they would fit into both of them. But a 0.7 megabyte block does only fit into the 1 megabyte rule. So that's what we call soft fork. And now we can have situations where we say we have a much larger space because we now allow 10 megabyte of blocks. And this is an extension, because now we have 2 megabyte block here. We maybe have an 8 megabyte block here. So this is very, very just for visualization purposes here, yeah. But then you also get the idea that also a 0.5 megabyte block might adhere to the rules of the 10 megabyte system. And this is what we called a hard fork. So that's the important part. And with this, you can think about, okay, hard forks are used to extend the system, to extend the states of allowed blocks, and soft forks always reduce the state of allowed forks. So that's the important part here. And for example, I think a very nice example for a soft fork, apart from that here right now about this block size discussion, is at the beginning, you know, from our transactions, if you remember, we have two fields here, and they are called script signature and script pub key. So, and this is a very historic term, or these are very historic terms, because they stated, it's in the transaction input here, tx in and tx out here, and these are historic terms because they were usually used, and if you look at the first blocks in the Bitcoin blockchain, there was only a public key stated here, and only a signature here. Why? Because at the beginning of Bitcoin, the idea of Bitcoin script was not there. So Bitcoin script was invented later, after Bitcoin has launched. And so they extended, or they did not extend it, they limited, because you could put anything in here. This was you could put anything in there. There was no limitation to that. But now, as they said, okay, we limit the space of allowed inputs there, we said we're going to introduce something new here, and this is our script. So what's going on there is it was reduced, and Bitcoin script was introduced as a soft fork to the Bitcoin network. So coming back to our exercise. Explain if changes require a hard fork or a soft fork, and explain the risks of changing this property only. So first of all, it's a hard fork, as I explained, because we're extending the set of allowed blocks. And explain the risks of changing this property only. So this is a question in terms of that aims at the question if the network splits. So this is where you have to think about, okay, are you able to get the community behind you and convince like 99% of the community to go with you and say, okay, we are increasing the block size? Or are you interested in creating a separate community, setting up new rules, and having your own currency here? And what's interesting here is that I think is the so-called replay attacks, and I'll try to introduce you a little bit to that. So usually we have blue blocks. So this is our 1 megabyte rule, and so it works as you would intend. These are our blocks, and then we decide, some person decides, okay, we are going to fork now, because these are now our 10 megabyte rules, and they build up on that. So these are much larger blocks, obviously, but apart from that, these are the same rules. So what would happen? What would happen here is if you would say, okay, I now have a transaction. I have a transaction here. This is my transaction, or this is a transaction where I received money. And now I want to spend this money. And so you have to imagine that these are two separate networks here. So we have network 1. This is our 10 megabyte network, and we have our 1 megabyte network. And they both have the same history. Why? Because they build on the same blockchain. So the money here you received in this block here is available in both networks. So if you would be able to say, okay, I wanna send this transaction now, I wanna send it in this network, then it would be included here, and some other party, probably the person you received money from, wants to get your Bitcoin also on the second chain. And this is very powerful because this transaction is valid here and valid here. Why? Because these coins both exist in both realities, in this reality here and in this reality. So they can be spent in both cases with the same transaction, with the same signature. And that's very dangerous because a lot of people and a lot of users are not really aware of that and say, okay, like I'm sending you here 1,000 euro equals 1 Bitcoin in this level and 100 in this network. And then they are exchanging these 1 BTC for a good, and it's worth 1,000 euros. So what happens here? You transfer it here. So this is a transaction. The person receives 1,000 euros worth of Bitcoin, and it relays it to the other network. And again, here is a transaction created that's worth 100 euros worth of Bitcoin Cash, or how you call the second chain. And so this is dangerous because now this person receives both coins on both chains and maybe has received more money than they intended to spend. So that's the reason why we have replay attacks here, and that's dangerous. And so what usually, if you wanna split the chain, then you have to build in some prevention mechanisms. So that's really easy. The most easy thing is you just have to include an additional field of transaction in the transaction, some additional information such that both chains are not compatible to each other. That's one issue. That's the replay issue here. The second issue we have is the hard fork issue. Hard fork itself, or a hard fork issue is a little bit it's not really on point. So the issue is that you now have the same situation as above. So again, we have blocks here. So I have no fancy notes app, so I have to deal with that on that. Let's just do it like this. And let's do it like that. So again, we have two realities, two hard fork out of any reason. So again, two networks here. And these networks are, as we saw up here, they use rules which are somehow similar, or they have the same rules except for one, which is the block size, for example. And this can lead to the following situation. If you have here, like, let's say we have in total here we have 100% hash power. Why? Because both of them use the same POW system, same hardware, stuff like that. So that's in total we have 100% over both networks. And now it splits up into following portions. So 40% here and 60% here. And this means, in this case, this is the 10 megabyte. Blue is the 1 megabyte rule here. So in this system, this will continue to work. Both worlds will exist separately, because these 40% do not accept the blocks of this one. But what is possible, because these 60%, so these guys with the red rule, they would accept the blue blocks. Why? Because they have a tighter rule set. So as 1 megabyte is always within 10 megabytes, 1 megabyte blocks would also be allowed here in the red blockchain. So what happens is, what could happen if this flips here again, that 60% of computational power is here and 40% is here. So this is state 2, so to say. What happens is that this chain down here, the red chain, could be orphaned. Why? Because your node says the longest chain always wins. So if the blue chain outgrows the red chain, and the blue chain also applies to the red rules, then obviously the blue chain is longer, the blue chain also applies to the rules, everything is fine, and all the nodes, all the red nodes would switch back to the blue chain. So that's also very, very dangerous. So therefore it does not happen, because people are aware of that, and they use preventionary measurements. So, but that could happen, that this chain gets orphaned very fast. So therefore, what people do is, when they have some kind of soft fork, they ensure that this will never grow back together. So again, some kind of do like this. Not very good at drawing, you get the idea. And what they define here is, this is your genesis block here. And what red, also the new rules define, they say this is our secondary genesis block. And only a chain which includes this block and that block is valid. And therefore, these two will always stay separated and will never grow together. That's what's going on there. So you need to really separate these two chains here. Let me see what I wrote in my solution, that I did not miss anything. Exactly, replay attacks, we covered that. Yeah, very good. We now have some questions on tweetback. Wouldn't the increase to 10 megabyte also decrease throughput and hence have negative effects on Bitcoin as a cash alternative? So increasing the block size does not decrease the throughput. Why? Because more transactions have space in a block, and this leads to the case that you can put more transactions per second through the network. What it definitely would increase the load of the network, and foreign regions where the internet is not very good, or I saw some guys doing Bitcoin via satellite stuff, then obviously this is going to get a problem or become a problem. But throughput is generally increased by largening the block size. Have there been any hard forks on Bitcoin or other Bitcoin currencies yet? So hard fork of Bitcoin are, for example, Bitcoin Cash, Bitcoin Gold, Bitcoin Satoshi Vision, and there are numerous hard forks or chain splits, so to say. But in terms of hard fork, and the chain was kept together, so we never had that for Bitcoin. So I did research that on the internet, but I did not found anyone claiming that a hard fork, as we define it here in the lecture, has happened to Bitcoin. Chain splits, yes. Hard fork, no. Are replay attacks also possible in case of soft forks? Transaction intended for the fork chain should also be valid for the original chain, right? So it really depends on if your chain splits or not. So your chain could split out of several reasons in terms of a hard fork, in terms of a soft fork. So there is no difference there. And if you basically what I told you here regarding this second Genesis block. So you could define this also in a soft fork environment, or with an update that is a soft fork, then it would also be possible that you have some replay attacks. But chain splits in generally could result from a hard fork, from a soft fork, and then you have the danger of chain splits, of replay attacks. Could we also say that larger blocks would increase the workload of full nodes, thus the number of full nodes could decrease, which could cause damage to decentralization? So larger blocks would increase the workload, and definitely, but 10 megabyte or 1 megabyte in 10 minutes is not too much of a problem. As I said, I think the bandwidth is the problem. But the reason for Bitcoin not to upgrade to that is, or to increase to 10 megabytes, and that was a argument used in the discussion when it was in 2018, where this discussion was going on, should we increase the block size, blah, 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 is that it does not change the problem. So the underlying problem is Bitcoin does not scale. Bitcoin does not allow you to include as many transactions as possible, or does not scale with the amount of miners or with the work put into the system. And changing it from 1 megabyte to 10 megabyte only puts the problem 3-4 years away. So that was the main argument. You need other solutions, just as increasing block size, because then you could further increase and further increase and further increase. And for example, Bitcoin Cash, I think, supports blocks up to 256 megabytes. And that's something I would say that's a little bit large for a truly decentralized network. If someone owned one BTC before the hard fork to BCH, how much BTC and how much BCH did one own after the hard fork? Exactly 1 Bitcoin and 1 Bitcoin Cash, or what BCH stands for. So that's a very easy. It does not. It's the same money as before. It's just named different. It's just in a different world. You could now fork Bitcoin to your local machine and say, okay, this is Bitcoin Uli now, and it's really in who believes in your fork of the chain. Wouldn't chain forking ease the feasibility of 51% attacks, since it's more likely that a malicious user is able to obtain greater percent of power in this fork? So that's if you looked at, for example, Ethereum, the next currency we will cover next week, had a fork, Bitcoin and Ethereum and Ethereum Classic, and this resulted in that Ethereum Classic has the same proof of work mechanism, but a very, very small network. So proof of work is much more easier. 51% attack is much more easier. And that's the reason what we looked at last week. If you remember, we looked at different exchanges and saw what their confirmation times is. And I think for Ethereum Classic, it was 1 week or so. So they got really paranoid that the system is getting 51% attacked. Didn't Bitcoin Cash increase block sizes to solve the problem of throughput? Exactly, it did increase the block size, but as no one used the system, the blocks never went full. So on average, their block size is smaller than in Bitcoin. I have a question about the Bitcoin Cash hard fork. If I have a BTC which was transferred to B before the hard fork was transferred before the hard fork, could I now still transfer it to BCH? So if you no, if the history of this certain date where the fork occurred is relevant. If you owned a Bitcoin before, then afterwards you own both. And if you did not own it before, then you do not own it afterwards. Very, very simple. Okay, let's continue. An adversary has more than 51% of the network hash power. Explain his options to attack the network. I think that's some of the biggest misconception I read out there when newspapers write about Bitcoin, something like that, 51%, is something that's commonly misunderstood. And the first thing what you can do with the 51% attack is you can block transactions. So as you're able to define the longest chain, you can block any transaction you don't like and block any block that would include that transaction and basically outmine it and orphan this block. That would be possible. And you can definitely put a denial of service on this blockchain. So you could still only produce empty blocks and also orphan all other blocks. What you can also do is you can collect all mining rewards. So all transactions, all other miners are basically cut out. And you can also do some kind of double spending pattern. So I think we covered this already in the lecture quite some time, how double spending works. But basically you create a reality where someone receives money, and then you orphan this reality by orphaning this block and mining around that and spending the money otherwise. And also very important for me is they cannot create coins out of thin air and they cannot change the rules. So that's very important. They still have to adhere to the system. And for example, they cannot steal, they cannot create transactions which are, for example, which takes the first Bitcoins that Satoshi Nakamoto mined. Something like that, that wouldn't work because you still have to adhere to the rules. But you can tamper with the history, and that's really, really bad. So 51% is very bad, but it's also very unlikely for Bitcoin. Inform yourself about the 51% attack on Bitcoin Gold. Explain what happened and how high the damages were, and how exchanges can decrease the chance of such an attack. So that is a question I asked last year, and it was very up to date because it was on May 18th, 29. And the communications of Bitcoin Gold director, the communications director of Bitcoin Gold went to the community and said, okay, someone is trying to use the 51% attack with an increased hash power to perform double spends, and advised you to increase the confirmations. So if you receive a transaction, the amount of blocks that builds upon the block your transaction is included in, That's called confirmations. So let's do a small example that you really get that. Box. Your transaction, 1 confirmation, 2 confirmations, 3 confirmations. So if that's the reality, 3 confirmations. So, or if that's the most current block, then it's 3 confirmations. So increase the number of confirmations such that you that it's difficult for the 51% attacker to rewind the history of your transaction. And so these suspected hackers who did the 51% attack sent Bitcoin Gold to exchanges and traded them for other cryptocurrencies, and withdrew from the exchange the other currencies, and then they double spent their own transactions that they initially, their Bitcoin Gold transactions, they sent to the exchanges. So the exchanges have sent the other currencies to the hackers, and the exchanges never received the Bitcoin Gold or could not use them anymore because the transaction itself was not included in the longest chain. So they got tricked into believing they received Bitcoin Gold, but they didn't. And that's something that's very important. Increase the confirmation time, monitor the network. These are ways to mitigate a little bit that, but obviously it cannot prevent everything. Moving on. Consider slide 13 in the slide deck. 06 Bitcoin assessment. Selfish mining is a process in which an attacker with less than 50% of hashing power can attack the network. Alpha defines the probability of the network choosing block 3A from the attacker. Explain the minimum hash rate required to launch a successful attack. If alpha is 100%. One of the, I think the topic of selfish mining is very difficult, and we receive a lot of questions because of that. And I'm trying to explain a little bit about that. But also, if you don't get it, it's not too important. Yeah, it's a theoretical concept. And I was on a conference in February this year, and one of the inventors of or the researcher who found this idea, or thought of this idea of this selfish mining attack, they had an update on this. They had a revised paper, so to say, and updated a little bit on that. And they claimed that there were cases of selfish mining in cryptocurrencies. They did not mention which network, they did not mention which currency, but they claimed that this is the case. And this is not a topic which is where the scientific community really agrees upon if it's possible, if it's not possible, if this is realistically, if it can be detected. So this is really a area where a lot of discussion is going on. So yeah, take it with a grain of salt. I find it an interesting concept. Yeah, but in the end, it is not what we really should focus on in terms of a real world use case. So let's take a look at the Bitcoin slide here. So selfish mining itself says that you withhold a successfully mined block from the network such that the other network has no chance to mine up on them. And the idea is, if you have 2 succinct blocks which are solved, then you can outrun the complete network in that second the other block gets created or gets published to the network. And I wanna emphasize a little bit on this question, because it's just can we do some kind of, I would like to draw on that. Is it possible? So what we have here is two possibilities. So possibility A is you found two verified blocks before someone else found another block on block 2 here. And in this possibility, you always win. 100% of the time you win, but you have two valid blocks, the others only have one valid block. You outrun them every time. So that's possibility A. A second possibility is that you have found a block, but did not found the next one upon that. And the network has found this block 3b before you have found block 4a. So in this is a race condition in terms of both of the parties publish a block at the same time. And now the question is who is going to get adopted in the longest in the longest chain. So on which block is block 4 going to be built up on. And this chance of being your block is described by alpha. And that's not a number you can measure, or this is not something that's out there, but this is just a hypothetical number. And you have also a possibility 3, the other party finds a block before you find your block, but then it starts over. So this is not a case that we have to keep track of. So you did not lose anything here. The case is that you could lose the mining reward here if block 3b wins. Otherwise, you always receive your mining reward. And now we have these two possibilities. We don't know how they are weighted. We don't care now because of this question. So we want to just know if alpha is 100%, what is the minimum hash rate needed to do this attack? So let's recap. We have possibility A, we always win. We have possibility C, where we are not able to find any block. Doesn't matter for us because we did not lose anything. And we have possibility B, where we would lose to a certain percent, or we win with alpha percent. And if alpha is 100%, then we always win possibility B here with this block. And we always win possibility A. So we win with A and B 100% of the time, no matter what our hash rate is. So our hash rate can be indefinitely small to selfish mine if alpha is 100%. So alpha will never be 100%, that's just a trick question from my side, so that you get a little bit that you think a little bit about the problem of selfish mining. Someone posted on Tweetback a link to an article on Vitalik Buterin's opinion about selfish mining. I think it's from 2013. So I did not read through it. I think I have to first read through it. Oh, okay. Colleague already published it. Yeah, you can look through it. So Bitcoin Magazine is I don't know about what's going on there, how to account for that. So take it with a grain of salt if you read it. I'll also have to take a look. Okay, that's it for the exercise sheet here. Are there any questions on this? I don't think so. One question, could you please explain again why it can never be 100%? So alpha describes this is not a value you can manipulate. So obviously if you're very well connected to the network, if other nodes mine on you, then this can be very high. But this is it's just a value for theoretical purposes. So you cannot really you cannot measure it. You can measure it afterwards, but not beforehand. And yeah, so it's a theoretical. If 100%, obviously it would be possible, but then the minimum hash rate is not your problem. Okay, let's move on. We have half an hour to spare. Let's take a look at the hardware wallet. So I prepared a little bit. That looks good. So we have our let's do it like this. Let's put this away. Let's do it like that. So this is my left screen. And what we have now is my mobile phone over here. So do like that. And I have to check that the browser does not really transmit the signal here. Looking good. So this is the hardware wallet I meant to show you before, and it's a Ledger Nano S. It's actually not that new, so it's I think 2 years old or so. So I got this quite early, and it's empty as of now. And if you look here, some very fancy Latin on here, viris et numeris. So Latin geeks can definitely answer the question what this is translated to English. And it has a small display. It has 2 buttons up here, and it has a USB port on the side. Apart from that, not too much to see here. Hardware wallets are a way of keeping track of your Bitcoins or Ether or any cryptocurrency you have. And I want to show that to you a little bit. So that you have a little bit of a feeling what's going on there. This is also connected to my computer, so I have some cable here. And as you see on my left screen here, this is my this is the software you need to use here. So no money down here on here, and this is Ledger Live, it's called, and it's used to interact with this hardware device. Why? Because on this device basically manages my private keys. So my private keys, we took, I think, already a look at how they are looking like. I can show you one in a second. And so this device needs to be tamper-proof in terms of that no one can read the private key out of it, but only allows the interaction through the software in terms of I need to accept it on the device. I need to enter pins, stuff like that. So that's very important here. So let's plug it in here, and as you see, it I hate it when I get called. Now my browser is working again. No. Sorry for that. Very good. Now it works again. So when we plug it in, I already set it up because it takes some time. When I would set it up, it would ask me for some PIN, and it also would require me to write down a recovery passphrase. So this recovery passphrase is similar to the one that you saw on in the first Bitcoin lecture. There's some kind of brain wallet stuff that's similar to that. So I already set up a pin, very complicated, 4 times 0. And now I'm in there. And as you see, it allows me to select between Bitcoin, Ethereum, FIDO Universal 2-factor, and some settings. And if I now want to basically install an application on that, then, or want to manage my applications because I want to put other cryptocurrencies on there, allow Ledger Manager, and now it allows to access that. And then you see, okay, I have a capacity of 168 kilobytes, so really, or 100, yeah, it's really a small device, not much data on there allowed, and now I can install some currency wallet on there, and sends it to the device and installs it. And now you would see here, okay, we now have the dash here. We could use that right now. And then we would have to add an account, for example. So I would say here, add a Bitcoin account. Add a Bitcoin account. I'm going to say Bitcoin here, continue. The device says, okay. I need to open up now the Bitcoin device here. So both at the same time, basically, allow me to press OK. And now it's synchronizing, and it creates a private key on the device for me, and also creates, so add new account. I can select between SegWit and native SegWit. SegWit is a other transaction format as pay to public key hashes. So pay to public key hash is a old way, and SegWit is a new way of doing that. But pay to public key hash is sufficient for us to understand how it's going on. I'm adding it, and now I have a new Bitcoin address, and now I could say, okay, I want to receive here, and the device tells me this is the address, so BC1, stuff like that, and I now have to check on the device itself that is identical with my with that what's displayed on the screen. And this is because this hardware, my computer, could have a virus, and someone manipulates that. But in this case here, I should confirm it with the device so that I know, okay, that's really authentic. And that's actually what's going on. And I could take this address, send it to someone, and someone could send me Bitcoin here. So unfortunately, I don't have any Bitcoin here right now, or Ether to really show that to you, how you would send and receive money here. And also the network fees are really high, so not too much interested in spending the transaction fees here. But that's basically the way how you would receive money. And if you would send money, this would also work the same way. So you would enter an address in there in this software, and this device would ask me to confirm that again with if the address itself is identical to the one showed on this display. So yeah, that's about it. That's about the device. You can use a lot of cryptocurrencies with that, but that's definitely not a product recommendation or something like that. So I don't get any money for it. It's just something that was lying around on my desk, and I think interesting for you to see. And this device is really for you to secure your Bitcoin, because I received one question now on Tweetback. This device you can now receive, so I could send me my own Bitcoins on this device and put this device in a locker or in some kind of safe and ensure that that my Bitcoins are not stolen. So this is a very secure way of handling your Bitcoins, and you can store Bitcoins and all the other cryptocurrencies. So this is the one of the safer ways to store your Bitcoins, or save your Bitcoins. Okay, that's about it. And let's continue with a little bit about Ethereum, I think. Turn this off. Turn this off. Let's get back here. So when we talk about Ethereum, Ethereum is also a cryptocurrency, as Bitcoin is, but the first main difference that is important to know is that it's account-based ledger. So the complexity from a Bitcoin transaction-based ledger with transaction input, output, stuff like that is gone. Obviously, our transactions have also some data fields. We will cover them in the lecture next week. But I think we forgot an important detail in when we first explained how transaction-based ledger works. So I want to talk a little bit about that for a few minutes or so. So let's look at here. So we have we have accounts and we have transactions. And you might remember that in Bitcoin we don't have accounts. And that's very important. Here we have accounts with some address here. Stuff like that. And we have transactions, regular transactions going on here. And we also say from A to B with some amount, 3 Ether, for example. And this transaction itself on Bitcoin is very easy because it can only be spent once. But when we have accounts and we do not refer previous transactions, then this account could basically have like 100 Ether. And the main issue that we don't know how often this transaction was actually executed, or that if this transaction was actually executed. So therefore we have one crucial part to that, and that every transaction which is from one account, from A for example, has a so-called nonce. And this is part that is included in the signature, and that means that every time A sends some money out there, we have a nonce, and this is a number that gets increased in terms of 1, 2, 3, 4. And this ensures that only each transaction is actually executed once. Because you can just, if you don't have this, you can resend the transaction to the network, resulting in another payment. So that's very important. That's one key feature of an account-based ledger, the nonce. So keep this in mind. We can take also a look at Etherscan. I think that's also very interesting to look really at the blockchain itself. Sorry guys, I'm having a little bit an issue here. I need a 5-minute break. I'll be back to you. Okay, sorry for that. Let's get back to topic, a little bit of fresh air, water. Oops. Okay, I was talking about Etherscan, to look here at the browser. And it looks like that. And what I wanted to show you is just the transactions itself. So if we look at the block here, we have 26 transactions. So this is Robson testnet because that's what we use in a second here. And if you look here, we have some transactions. We have 26 transactions here, and they usually have some transaction hash. So this is just a unique identifier, so to say. And we have a from address to a to address, and we have a value and a transaction fee here. Now let's take a look at, for example, this transaction. And you can see we have a from to value, as I said, transaction fee. That's a little bit more complicated. We will do this in future transactions. And what we have here is a nonce, and this is the unique, this number used only once for this transaction, so that it does not get really double spent. There's also a input data here, and but that's also for future times. That's what is going on here in terms of a account-based ledger. What's also important is that we now have not only accounts, so it's not the main difference, the only difference that we switch from transaction-based ledgers to account-based ledger, but we also now have the opportunity to use smart contracts. And this is basically code stored on the blockchain, which also has a unique address. And basically, if you send a transaction to this smart contract with some data, then this code gets executed. And on Etherscan, you see it because of that little contract symbol before. And you can take a look here and see that example. That looks better. And that's the code that is stored on the blockchain. It gets executed every time you call it. That's the idea here. And I want to show you through two applications that we use throughout the semester, or we won't use it that often because we have a lot of theoretical questions, but that you get a little bit of familiarity, that you can know how to use the software here. The first one is Metamask itself. Metamask is a software which is basically a wallet inside your browser. So you can go to metamask.io, and this metamask.io allows you to install this browser here for Chrome, and you can also use Firefox if you want to, and then you get this little symbol up here. So you have to do a little bit of setup, account setup, stuff like that. But the most important part here is what we are going to use here is the network. Ethereum basically has the main network where all the real money is, but also has test networks. And we are going to use Robson. And if you want, because if you create an account, you don't have any Ether to start with, you have to go to a faucet. A faucet is a website which gives you free money, so to say, on this test network, because it isn't worth anything. And you can go here and say, okay, request 1 Ether from faucet, and they will ask you to grant permission to your Metamask. So you need to have Metamask installed and then receive new money here. So this is a testnet transaction on the Robson testnet pending, and this is what they sent to me. They now sent money. And this is what I also would recommend to you. Go through Metamask.io afterwards, or use the time and install this little fox here. And then you can also switch, you can create new accounts, you can switch between many, you can switch the networks. Obviously, you see I have 0 Ether right now on the mainnet, but on the testnets I have hopefully 2 Ether. That's the first thing. Try it out, see for yourself if you get something. I tried it last year to do it live with all my students, with all of you, and it's a little bit, it crashes a little bit in network, so we have to be a little bit careful about that, doing it all at the same time. And the second part I want to show you is, apart from Metamask, I want to show you a little bit around in Remix. And Remix is a, maybe we can do it like that, so that it that you see how it works when you start it open. Remix is an online IDE that allows you to write smart contracts in Solidity, the programming language we're going to use in the next weeks. You have a lot of features that's not really important for you, but there is, I want to show you a little bit around what's going on here. I will also not talk about the source code itself, because we will talk also about that. I just want to give you an impression of how you use it. So first of all, you need to select an environment. Environment means which programming language are you going to use, and you should always click Solidity, otherwise you won't be able to compile or run your smart contracts. And then you have the option here to click New File. You can name it however you want, and this is your, so to say, your IDE. You see here on the left are the menu points. The first one is your what files you have here. Second of one is how you compile, so your compiler version, stuff like that, and also that you your settings on how to run the smart contracts here. But I'll go through it step by step. So first of all, we have our code. I also prepared a small example here, which is really not too complicated. We have basically a smart contract with stores an owner. This owner is stored at the beginning, and we have the opportunity to set a single unsigned integer. So this is a date type unsigned integer data, and it's stored in the variable here. Very simple example. You don't have to get it right now. I'll just you can come back later to this video and execute it for yourself when you got the basics of Solidity, because then you know how it works, and this is the important part, how you can execute it. Now you want to check if this is your code, you wrote this like that, you want to compile it. So we go to the compiler here, you select some compiler you like. We don't make any I have to check which version we use in the lecture, but we won't judge you, or we won't give you bad grades because you missed some version specific details in Solidity, so that's not really important. I'm going to use here 4.26 right now for this example, and you have autocompile in there, so that's very good. It compiles every time you change something to the code, and you can press compile and it recompiles it, and you see the green check mark here. So that worked very well. Your source code compiled, and you can see also the compilation details here. So that's all the information the compiler put out there. Not too important right now. If you want to run it, then you have to go to this menu point, deploy and run transactions. So before you start executing a smart contract, you need to deploy it. We use here now a JavaScript VM. That's very good because that's just inside your browser. You don't have to have additional software, and you have many accounts which all have 100 Ether. So you can switch between them and use them. And we now just use the first one. And what we do here is we have some information about this, about the transaction, and we have this contract, and we can now press deploy, and we get a green check mark down there. That's a log from our transaction that was executed, worked because of the green check mark. So as I said, you will get all the details. For me, it's important that you know the workflow, where to click, where to see the details. That's the most important part here. And now you see here down deployed contracts. And this is the test contract here because it's called test. And now we have 3 buttons here. And these are the yellow ones are setter methods. So they allow to set something. And the blue ones are getter methods. So they will allow to get out of the smart contract information. So for example, we have an owner. The owner is this 4C35. That's also the 43C. That's my account I created this smart contract with. And this data here is now empty, should be empty. So that's empty. So we can execute this locally on our machine. So we do not have to create a transaction for this. And if we now want to set the data, that would also be possible. You see again, the transaction gets executed and you receive the data again and it's updated. So that's the magic of this interface. And also what's important here is, I want to mention this briefly, if you want to not run your JavaScript this locally or your source code locally or your smart contract locally, you can use inject web3. This means that, so you don't see that, I'll do this like that. You see this little Metamask notification window here. That says, okay, Remix wants to access your Metamask and wants to use that. And we can allow that just for, and now we are using the injected web3. What does this mean? We use the Metamask we have set up in our browser. So as you see, 0xd8f, and it's also identical to that one. So what we can do here, we can now with our 2Ether deploy this smart contract on the blockchain. Let's do that just for fun. Now I'll have to, that's a little bit unfortunate because I have window capturing on. What now happened is that Metamask has asked me to create a new smart contract. And now this is the browser add-on, so to say, and now I can accept or decline if I want to really execute this transaction. And I want to do it. It's gone now. And what I now am able to see here is that actually my smart contract was executed. And if I see here, I want to copy the transaction ID, or I copy my account, and I go to Robston, our Robston test network Etherscan version, put in my address, and see Uli has received 2 Ether, one 8 minutes ago, one 2 hours and 26 minutes ago, and he actually created the smart contract on the blockchain. So you see here, this is the smart contract now at the new address. And what you also can see here is my nonce. Why is it 0? Because it's the first transaction of my account. These both do not count because they're transactions towards my account and not from my account. So that's the important part here about Metamask Remix, about finding that on Etherscan. So try it out for yourself, see how it works. There are also some example code in there. So Remix also has this storage owner ballot stuff is already in there. And yeah, but take a look and see if it works for you. And apart from that, we see each other next week with the lecture on Bitcoin, on Ethereum basics. And then we will talk on Wednesday about the exercise sheet, talk a little bit about the theoretical implications, and look into that.